C. Okay, I'm going to choose that A. Whatever it is, I'm going to choose it. Now, if I change the curve, right? If I change the curve to a different curve, I might have to choose a different A, right? My A will depend on the curve. You give me the curve, I'll find the A. You give me a different curve, I'll find a different A, all right? So I've chosen an A, I've got a circle in there, all right? Now, what am I going to do? I'm going to split this up, right? So I'm going to, let's call this curve here, right? Let's call this circle, let's call that C2, okay? And just to make things easy for us, let's go back and call this C1. C1, C1. That way it matches the formula we just did, right? With the hole, the region with the hole, we had a C1 and we had a C2. Yeah, but this direction is backwards, right? So let me scroll back up to what we concluded there. We said that if somebody gives us a region D with a hole in it, C1's counterclockwise, C2's clockwise, then the double integral, right, double integral of partial q with respect to x minus partial p with respect to y turns out to be this line integral, the sum of these two line integrals, right, over C1 and C2. We're going to have that formula, but since our C2 is in opposite direction, this is what you pointed out, this is going to be a minus, isn't it? You all got that? So what I can say here is that this C1, sorry, F, no, let me do it this way. Do it this way. I'm trying to think of how I want to do this. The original thing we're looking for, right? Let's start with that. The original thing we're looking for, right? The original thing we're looking for is this, right? Which is also, just so that we have notation, this is the line integral over C1 of P dx plus Q dy. Do you all agree with that? Just by the definition, if I change the name of this curve to C1, then when we started everything out, that's what we wanted to know, right? And that notation just means this. So I'm not having to use any Green's theorem, I'm just writing down exactly what it is that we want to know, right? But if D, right, D is region bounded by C1 and C2, right, as shown there, what we have is that the double integral over D of partial q with respect to x minus partial p with respect to y dA must be equal to the line integral over what? C1 of p dx plus q dy. Careful. Minus, right? Not plus. Minus the line integral over C2 of p dx plus q dy. That's from the result that we just got in the previous note, right? Do you all buy that? All right. What now? What now? What now? What now? What is this? What's the partial of q with respect to x? We never even looked at that. What's the partial of q with respect to x? Let's see. What's the partial of q with respect to x? So what I'm going to do right now is I'm going to focus my attention on this right now. Do y'all see right here? Do y'all see what we're trying to find is in here? Do y'all see that that is this? Do y'all see it's in this formula? So if I can figure out what this is, and I can figure out what this is, then what do I know what that is? Okay, this right here, let's do that. What is the partial of p with, or sorry, partial of q with respect to x? Write it down here. Partial q with respect to x is, This is P, this is Q, right? So quotient rule, yeah, quotient rule on that. So derivative of the top, 1 times the bottom, minus the derivative of the bottom, 2x times the top, all over bottom squared. Which is, see, x squared plus y squared minus 2x squared. So I think that's y squared minus x squared. Right, do y'all believe that? Do y'all believe that that's partial q with respect to x? Yeah. Okay, what's the partial p with respect to y? It's going to be another quotient rule. Derivative of the top, -1 times the bottom, minus derivative of the bottom with respect to y. 2y, and then times the top, -y, all over bottom squared. All right, what do we get up top? Negative x squared. And then we have negative x squared minus y squared plus 2y squared. So plus y squared over bottom squared. And they're the exact same thing. Yeah. So what's partial q with respect to x minus partial p with respect to y? 0. It's 0, right? It's 0. Follow? So this is 0. And the double integral of 0 is just 0. So we just get 0 here. Equals this, right? All right, y'all still with me here? I'll run back through it if I need to. The original problem, right? I changed the C to C1 because of my drawing, right? I want to show that that's 2 pi on that field. So I drew my C, arbitrary, contained the origin. I called that C1, went counterclockwise. I drew a circle in here of radius A. I called that C2. And then I could write this line down right here, right? That calculates to be 0. So that means these two subtract to be 0, which means they're what? Just add this to the other side, right? That means these are equal, right? And it turns out that this right here is actually what I'm looking for. That's the original integral I'm looking for, right? So let me get to that. Since those added up to be 0, that was very, if it was a different field, like if this did not add up to be 0, then this problem wouldn't work. This has to add up to be 0 for this problem to work. So now, this line, I can say now that the line integral over C2, right, of P dx plus Q dy must equal the line integral over C1 of P dx plus Q dy. And remember, C1 was arbitrary, right? That was the arbitrary curve that I drew. That could be any curve, right? But this is not arbitrary. This is a circle of radius A, isn't it? A circle of radius A. So if this is a circle of radius A, then can we actually compute this? Can we compute that? Yeah. What we're going to do, let's look at C2. C2 looks like this. The radius is A, isn't it? What's the parametric to draw this? A sine t. Y is A cosine t. And t is between 0 and 2 pi. Right? Oh, wait, yeah, sorry. Why did I do that?
Would it matter?
It wouldn't in this case matter. It would still draw that circle in a counterclockwise, so that would be okay. But I'm going to go to our convention here. Sorry. All right, so now I'm going to do this. Okay, I'm going to do this right here. All right, now this is going to be tricky. All right, it's going to look a lot worse than it is. Unless we want to do we want to try Green's theorem on that? Can we do Green's theorem on this? Can we do Green's theorem on this? Do y'all see what I would have to do for the next step? For P, I would have to plug into P what? For Y, I'd have to plug in, right? Right? Okay. So,
is that the one, are we gonna like let P equal 0 and Q equals X?
we're not looking for the area of something.
Okay.
Yeah.
I'm getting confused.
Yeah. That special case, only look at that when we're trying to find the area of something. My question to you right now is, can we use Green's right now?
Yes, because we have a parametric and we have a closed bounded linear integration.
Okay. So what would be the formula for this then? See, because is this D? This isn't D, is it?
Yeah.
This is not D. D is that whole thing, right? I could call this like D prime. Let's call it D prime. It's not a derivative, but it's not D. D was what? The one with the hole in it? I'm sorry, the one with our hole, that was D, right? And then that was D prime in the middle. Let's try just the direct computation. Let's just try it. It looks terrible, but let's try it. If we just did this integral right here, it would go from 0 to 2 pi, right? What's P? It's this, right? But you have to replace all your x's with a cosine t and all your y's with a sine t, right? Why did I put two t's there? All right, what's the top? Negative a sine t over, okay, x squared plus y squared. This is actually good. It's this squared plus this squared. So we'll get an a squared cosine squared, a squared sine squared. So you'll get an a squared, right? Because you factor out a squared, you get cosine squared plus sine squared, you just get a squared. So that's going to be a squared here. And then you have dx. What's dx? Negative a sine t. I don't want to erase that. I'm going to continue, plus, so I'm going to do it just a final at the end dt here. Let's do this one. Q dy. So Q plugged in, what's the only difference? On top you have x, right? So a cosine t, and then on the bottom a squared again, and then when you take the derivative dy, right, dy, here we go, you get a cosine t. What do these two multiply to be? A squared sine squared t over a squared, and the other one multiplies over here to be a squared cosine squared t, right? They have the same denominator. I put them together. I get 0 to 2 pi. I get a squared sine squared t plus a squared cosine squared t all over a squared dt. And the top, you can factor out a squared. You get a 1. A squared over a squared is 1. So you get integral 0 to 2 pi of what, a squared? Oh, sorry, a squared cancel, 1. 1 dt, and that's just 2 pi. So what we were able to show is that the left side was 2 pi, right? And then that means that this is equal to 2 pi. which is the original thing we were asking. So we wanted to know what this was, and we found it was 2 pi. And our C1 was arbitrary, completely arbitrary. Now there's a lot going on here, and I understand if you're confused in it, it's okay. Hopefully you followed it. Really, it's more, like I said in the beginning, it seems like that problem can't be attacked because you can't show it for every curve because you don't have enough time in your life to write down every possible curve containing the origin. But by doing this thing of drawing a circle inside and using this theorem, you actually can do it. Okay, yeah. We are done with this section. Are there any questions?
Yeah.
Yes?
Couple.
Yeah?
So I'm getting confused about the whole area thing.
The special case thing?
Yeah.
Okay.
So, well, we started off with saying positive orientation is the closed curve over some region D,
Yep.
right? So then you can go from a line integral into a double integral
Yep.
with respect to dA.
Yes.
So I guess that's where I'm always getting confused. 'Cause
Okay.
And in this case, we weren't referencing area, we're just referencing E.
Okay, yeah, let me, I'm not going to go up to notes, I'm just going to find some blank space here, just to recap, because this is it, we're not going to do any more today.
Okay.
The next section is curl and divergence, and we are where we need to be right now in this class. So, all right. So what we said is, if you start out with a curve, right, C, right, with positive orientation, that the line integral over that closed curve C of f dot dr is the same as the line integral over C of p dx plus q dy. That's just notation, right? But by Green's theorem, this is the double integral over d of partial q with respect to x minus partial p with respect to y dA, right? Where d is the region enclosed. So that's Green's. You go from a line integral to a double. All right. To use this backwards, what we were saying is, when can you ever go from here to here, right? Well, we said there's a lot of different ways to go from here to here. The one thing we are going to look at, there's only one scenario we want to look at, and that is this very special case where this turns out to be a 1.
Yeah.
Because if that's a 1, this side over here becomes the double integral over d of 1 dA, right?
Yeah.
Which is just the area of d. So if I ever wanted to know what the area of some region was,
Yeah.
then there's a way to go from here to a line integral, right?
Yeah.
This can go this way now and become the line integral over that closed curve C, and then either one of these, right?
Yeah.
I'll do p dx plus q dy, right? But then I need to know what p and q are for me to do this. And p and q, right, d, we start out with d. They give us d, right? D is here. And then we go and we say, okay, well, what's the c that draws d, like goes around d,
Yeah.
right? But we need to know p and q to do this. Well, what p and q do you put here? Well, any p and q that when you do this, you get a 1.
Yeah.
So we said if you let p be 0, you let q be x, that is one scenario where when you do this, you get 1, right? And now you know what p and q to use over there, right? You're just going to let p be 0 and dx, q be x. So this now becomes x dy. And that's like the master formula right there.
Yeah.
If you want to know the area of D, right? You want to know the area of D, some area of some region. If you can draw the curve, if you can come up with a curve that draws draws around it, then that's the line integral you have to do.
Okay.
Okay?
Yeah.
So in the problem that we just had, we were not doing that because we started out with this side, right?
Yeah.
We wanted to show that this was equal to something.
Yeah.
So we have to go, here.
Yeah.
We can't do the special case because this is really just one particular usage of this.
Yeah.
That help?
Yes, and then in this case, the parametric had a bunch of functions that ended up equaling 0, right?
The parametrics.
Because there was negative y over x squared plus y squared, and when we did the partial derivatives, that was 0. That was not equal to 1.
Yeah, that was 0 over here,
Okay,
right?
Yeah.
But because we had broken it up into two pieces, we had that the sum of two line integrals equaled 0. Well, it was the difference because we had a minus in there. So we had the difference of two line integrals equals 0. So we moved one to the other side. And we said then they must equal each other.
Yeah.
And one of the two, we don't know what it is because the curve was arbitrary. The other one, the curve was the circle.
Yeah.
So we found that was 2 pi, and that
That makes
must,
sense.
yeah.
Okay, I understand now.
Yeah. Okay. All right. So yeah, I don't want to get into the next section. The next section I think is going to be pretty smooth. Let's go 5 minutes. Is that all right? 5 minutes. I want to start making you think about something that's coming around the corner. Because I know we're going to get a little hung up on this later. So remember this, that if I write R of t equals, let's go back to this form, cosine t, sine t, t between 0 and 2 pi. What does this draw me? Circle, a curve, right? A curve in two-dimensional space. A curve in two-dimensional space. So it draws me this, it draws me this curve like this. And it actually goes like that. But that's what that is, right? That's what that is. Now, what if I change it and I do R of t is cosine t, sine t, t between 0 and 2 pi. Yeah, it's like a spring. This is three-dimensional now, isn't it? In the two-dimensional space, it draws you a circle, but then the z-coordinate is growing linearly. So it draws this circle, but it comes out at you at the same time. So three-dimensionally, looks like that. Well, it only goes around once. But if we were to keep doing it, right, if we just not restrict it, it would draw this spring. But the idea here that I really want you to understand is that these are curves, right? These are curves. So what if I wanted you to draw me this? I want you to draw me that disk. But I don't want you to give it to me like an inequality, because let's say the radius of this was 4. Okay, what if I wanted you to draw this for me? I don't want you to write this down. This is correct. This is a set of inequalities that represents that disk. It tells you all the x's and y's that satisfy this live in here, right? It's basically all the circles with a radius between 0 and, wait, hold on. 2. No, this should be 2 here. Yeah, sorry. Right? No. 16. This is 16. I apologize. That's my radius is 4. Another one. I'm getting a lot of them today. Okay. Yeah, so right now there's no easy way to draw a surface, right? Other than using inequalities. Can we draw them with vector functions? And the answer is yes. And this is what I just want you to think about this. I'm going to leave you with this. I'm going to come up with this vector function r, right? And normally we only plugged one thing in, right? T was called the parameter. T was the input. And then what would come out would be their 2 or 3 dimensional vector. What we're going to do now is look at a vector function that takes in 2 parameters instead of 1. Instead of just taking in t, it's going to take in 2 things. And we normally call them u and v. Yeah, let's do it. U, comma, v. So you're going to plug in 2 things, u and v, and somehow that should draw me a surface. Now we're in 2-dimensional space here, so I'm going to have vectors, right, that are in 2-dimensional space. Now, think of it this way. You need to draw a bunch of circles, don't you? You need to draw all the circles that start with a radius of 0 all the way out to a radius of 4, don't you? Well, how would you draw me just the outside circle? What would you put? You put 4 cosine t, you put 4 cosine t, and then you put 4 sine t, right? But that's what you would normally do, right, over here? But see, we're not using t here. What are we using? U and v, right? So, okay, I'm just going to change that to u. Is that all right? Now, this should draw me just the outer circle. But you see I've only used one of the two variables I have, right? So right now I would say u is going to be between 0 and 2 pi. That would draw me just the outer shell. But I want all of them, right? So I actually want this to change, don't I? I want that to actually change, not always be 4. I want it to change between what? 4 and 0, right? Well, do I have any control over another variable? Yes. I have the v as well now, right? So I'm going to put a v here and a v here, and I'm going to let my v go between 0 and 4. And now what happens is you can imagine this a couple of ways. First, you can say fix v at 0. If v is 0, what do we get here? 0, 0, that's just the origin, right? So if v is 0, you get the origin. Now let v be, let's say, 1. If v is 1 and you let u go between 0 and 2 pi, what do you draw? Unit circle. Then you let v be 2, right? And then you draw. And then 3 and draw. And then 4 and draw, right? But it's every value between 0 and 4. So all the little fractions and decimal. So it draws you all the circles, right? It draws you all the circles. That's how we do it. That's how we do it. So what we're going to need to be able to do as we move down the road here is draw surfaces, not only in 2-dimensional space, but in 3-dimensional space. And not just circles, but all sorts of different things. And ultimately what's going to happen in here is I'm going to give you some shape. Like this. I don't know. Do it like this. Like some 3-dimensional solid like this. Do y'all see that solid? It looks like kind of like a cylinder. And then the bottom is like a plane. And the back side is like a semicircle. And this front side is a semicircle that's been tilted over. Do y'all see that? What we're going to have to be able to do is come up with a vector equation to draw each of those surfaces. The bottom surface, the front surface, the back surface, the top surface. We're going to have 4 different surface vector functions. And then we'll be calculating things like, we'll imagine that this is sitting in a vector field. But we have to be able to draw the surface first. Just like back here, we had to be able to draw C, right? To do line integrals, we had to be able to draw C. We have to be able to draw a surface if we're going to do anything with this thing called flux later, okay? So just something to think about. I wanted you to see it for the first time, and let's have a good day. Wednesday again, I'll be here. You're not going to hurt my feelings if you're not here, but I'm going to record the class as long as I'm feeling okay. And check your email just in case. If I start feeling bad, I'll send you all something. No mini exams, right? You got some time off. So you should be able to do your homework up through the section we just finished, 13.4. Have a good one, everyone.